Okay, so I thought I might go over some recap from last time. And so, okay, I don't think it makes a lot of sense for you guys to try and copy that into the notes because it's all things I said before. But I thought it might be useful to have a look again at what we did, what we planned to do, and why we did the things we did. So, okay, the whole setting, right, is that we saw these plots of the spectral form factor for specific triangles on hyperbolic space. We were specifically looking at the modular domain. And we saw that, well, I told you that the spectral form factor had this exponential ramp instead of the linear ramp that is usually there for chaotic models. And the goal of the lectures, at least for today, is to try and understand where this exponential ramp is coming from. And the tools we want to use for this is periodic orbit theory, where the spectral form factor k is related to a Fourier transform of the two-point function of the density of states. And using periodic orbit theory, the general lore of periodic orbit theory is that you have the way in which the density of states is a function of the energy is through some average behavior and some oscillations on top. And periodic orbit theory is about trying to understand this function here, and we are going to compute it specifically for the case of these of the modular triangle onto the hyperbolic space. And what it usually looks like in chaotic models is something like this, where yesterday I went over these different ingredients in this formula, but hopefully whenever we get to the formula, we'll be able to identify the various ingredients and understand somewhat how they came about in the specific setting. Of course, you could also try to derive this formula, but then you need to go through a lot of more steps. Okay. And so, of course, we want to use this afterwards, and I don't know if we will have time today, but if we don't do it today, we'll do it tomorrow, to plug that into the form of the spectral form factor and derive that. Now, the whole point of periodic orbit theory, one thing I didn't say yesterday, and that might be good for general knowledge to mention, is that basically this type of formulas came about thanks to Gutzwiller, and the whole point was that they were trying to do something similar that I guess all of us have seen in maybe undergrads, which is known as Bose-Sommerfeld quantization, that is usually applied in an example on the harmonic oscillator to try and understand how this linear spectrum comes about from the simple periodic motion in the classical theory. So usually whenever you see Bose-Sommerfeld quantization in integrable models, you see it applied to the harmonic oscillator. It's a very easy exercise to do, and you see how from the classical motion you understand what quantum eigenvalues of the spectrum are. Okay, so this formula is trying basically to do something similar, but of course you don't have this periodic, the dynamics is not nicely foliating the phase space on tori as in integrable models. In chaotic models, it's much more complicated, but still this formula tells you that you can use periodic orbits that are appearing in this chaotic dynamics as skeleton, if you want, of the dynamics to try and understand the spectrum. Okay, not going to use more words on this. And so the point is to, compute these oscillatory parts for hyperbolic billiard, plug it in, do the Fourier transform, and find at least the early part behavior of the spectral form factor. So this was the domain we were looking at before. And I remind you that we're trying to solve this eigenvalue problem, so the Laplacian free motion on hyperbolic space onto the hyperbolic space with these specific boundary conditions that this is the fundamental domain of the motion. And we saw, given that we want to use periodic orbit theory, we had a look at the geodesics, the periodic orbits on this domain. And while we saw that for every geodesic that is not necessarily a periodic orbit, you could find matrices in PSL2R that were leaving this geodesic invariance. Only the matrices in PSL2Z as opposed to R were actually leading to periodic orbits on this. So that was the last part of yesterday's last lecture, was to understand that PSL2Z the matrices leave the periodic orbits in this domain invariant. And whenever you try to compute their length, they turn out to have a very specific behavior. The relation of the length to the matrix in PSL2Z that leaves it invariant is as follows. So given that this matrix only has integers, is only made of integers, its trace will also be an integer, and you find only specific values of the length that are present in the length spectrum of the periodic orbits of this theory. That was the recap. And now we're going to use this to try and derive the oscillatory part of the density of state. Of course, as I was hinting to before, it can be quite technical. So what I'll do is I'll try to focus on the important steps, how we use the periodic orbits and so on, how we try to compute the necessary things. But whenever there's like some integral or so to compute, I'll remove it, or I'll move it to the tutorials, and whoever is interested can come there, and hopefully we can have some things done there. Okay, so that's the plan. Is there any questions? Okay. So the first thing that I'll do, and it's immediately the one of the main aspects of this story that will lead to the exponential growth. It's the fact that the periodic orbits in this type of triangles have exact degeneracies in the length spectrum. So usually in chaotic models, what happens is you have, for a given length, you will have one or at most two periodic orbits of the same length. And then in computing the spectral form factor, well, it'll be important that you have almost no degeneracies. And in this case, the story is completely different. In this case, you have an exponential amount of degeneracies, of exact degeneracies. And that's the key feature that will lead to a different spectral form factor. Okay. So how do you see this? So it's a generic, it's a generic feature of chaotic models that the total amount of geodesic with length below a certain value, so let me call it n, of lengths below some big value L, grows as the exponential of L over L, and there might be some coefficients here, but in our case, these coefficients are just 1. So that's, I guess I'll just write an inequality to, but it's really an asymptotic, well, maybe I should keep that. It's really some asymptotic behavior as L goes big. And of course, in generic systems, in generic chaotic systems, you can have a bunch of different values that L takes, but in this case, right, it's not true. You have only very specific L's, and the sum of all of them below some value L have to grow up to grow in an exponential fashion. So then a question you could ask is, okay, given that I know this behavior, I didn't derive it, right? I'm just telling you this generic behavior in chaotic systems, and specifically for the modular domain, you can show that it takes this form. So then you can ask, what are the degeneracies at a given L? And so to do that, it's very simple. You just have to, given that all of these values, all of the integers will be realized, what you just have to do is at some given, maybe I should call that n hat. So this is just some integer n. At some value of n, you will have some value, nothing special here, but the degeneracy at this specific value of n will be exactly this number minus what it was if you just subtract 1 unit to this n. Right? That would be the degeneracy that you have at exactly one value of n, but also at one value of L. And so the exact degeneracy grows in this way. So then to compute this, because at large n, the different L's will be super close by. So this you can see by just plotting this function as a function of integer n's. So the L's will be lumped together in some exponential way. And hence this you can approximate basically by the derivative of e to the L n over L n by the n. And then here, well, we're considering a small step of 1 unit, right? So we're basically, say, Taylor expanding one of the two. And when you compute this, you find that it grows like this. Okay, of course, depending on the value of n you're looking at. So you see that the degeneracy, just by the simple argument, this degeneracy grows exponentially with L, which will be a crucial fact. Okay. So now, is there a question regarding this? So for normal systems, again, you don't have this exact degeneracy because L can be taking any value, basically. And as a result, you very rarely have exact degeneracies, except if you have like some time reversal symmetry that will map one orbit into its time reversed one. So at most, usually you have 2 as a degeneracy at a given L. So that was just some intermezzo. It was basically the end of the story I was explaining yesterday. And what we now want to do is compute the oscillatory part of D. Okay, so how are we going to do that? We're basically going to use this formula here, which I wrote for convenience because I'm not going to derive it here. But if you're interested in the derivation, those are the 2 steps that maybe require some inside information if you don't know how to start. But if you're interested, I think that we'll also do in the tutorials. So, okay, have a go at it if you want to, and if you're interested, just come to the tutorial session. But the main point is that we want to use this formula here for the total density of states, where this guy here is the Green's function of the problem. So I wrote here one representation of this Green's function. That's not the one we'll be using. We'll be using the more usual one that you may be familiar with, as in that it has to be a solution to the inhomogeneous delta function sourced wave equation. But of course, this is useful to prove this fact. Okay. So, and of course, the goal will be to try and identify, but it won't be so hard to try and identify the oscillatory part and the mean part. And of course, we want to use periodic orbits to define the oscillatory part. Okay. So, to be specific about the words that I was using before, we're going to want to compute the Green's function for the modular domain. So it will be a solution to this equation, so the Laplacian plus the energy. So the energy here is this thing. But we will exclusively work with D as a function of E as opposed to D as a function of K. The two just differ by a chain rule. That you can easily make the argument for. Okay, so. Okay, so this is the equation we want to solve for this guy with, of course, the boundary condition that should be periodic on this domain, and every point outside can be mapped to inside with a group element of the modular group. Okay, so we will be using a method that is commonly used in this type of problems where the domain you're interested in is the quotient of some bigger domain by some discrete group, namely the method of images. So to do the method of images, what you'll do is you'll define the guy you want as a sum over the guy on the bigger space, which would be 2D hyperbolic space, which maybe you want to, I'll just call it H2 here. But then you want to be summing over all the group elements that you're modding the whole space with PSL2. And the reason you have to do that is because you're in, like this G, the Green's function is a measure for how information propagates from, like roughly propagates from one point to another one, Z to Z prime, but then all the other points on the domain might be related to this Z prime, and you have to take this effect into account. The fact that all these other points are also identified with this Z prime in the fundamental domain. So, okay, standard method. I'll just maybe write it for reference. And so we will use basically the fact that this guy is a known function, so we won't derive it. But of course, you're free to try and derive it or look it up to see that you trust me on this. Oops. And I'll tell you what it is now, so that we will going to take for granted. So the way you would compute it is by solving the homogeneous one and then taking linear combinations so that the homogeneous one, and then take linear combinations so that when you integrate, you would get this delta function contribution. So it's a standard method, but it requires a bit of effort, so I don't want to lose time with this right now. But perhaps I'll put it in the notes. An important fact to notice is that because the Laplacian is invariant under all the, because the Laplacian has an isometry group that is all the fractional linear transformations that do not change the distance, you know by usual arguments that the solution to this equation will only be a function of the distance on this space between the 2 points you're considering. Okay, and when you do the computation, you see that it's true, but you could expect this from general principles. And so the distance between any 2 points on the upper half plane can be written as follows. So here it's all, like this is also something if you wanted to, we could compute in the tutorials. Yeah, it's written like this. So the cosh, this guy here is 1 plus Okay, so for those who might not see what's written here, it's basically the same as with the x's, with the square and everything, but for the y's. Okay. So that would be the one just for two-dimensional hyperbolic space. And then we need to apply the method of images to this Green's function. Oh, and it has, because this, sorry, nobody told me, but I didn't tell you what this Q is. So this is known as the Legendre function of the second kind. Okay, and there is an integral representation of this guy, which will be more useful than what it now looks like. But might be a bit scary still, but okay. Okay, So this k here, yeah, I didn't write it down, but I'm pretty sure it's just this k here, but I should check. Okay. And yeah, it should be the same k. So at this point, this is all just information. We didn't derive anything. But this is what we're going to work with, okay? Okay, so a very common fact about periodic orbit theory is that the mean density will come from the geodesics of zero length. That's the way you do it in just a Gutzwiller formula, and that's the way we're going to do it here as well. So that means that we have to look in this sum here in the method of images. We have to look at the identity element. Why? Because if you look at this formula here, what appears here is Q to Q, right? So whatever connects Z with G of Z, because Z prime becomes G, becomes C, is G that is the identity element. So the identity element will give you the density of state because it's the thing that will not have any oscillations. The oscillations will be coming from something like the exponential of or the cosine of something times the length, and if the length is 0, the oscillations go away. So we will first have a look at the average density of states, and the point is you have to look at G as the identity. Okay, is that clear? Yeah. Yes, that's right.
And then you are building the green function out of summation over G acting on one of the...
Yes.
So if I apply here, all of them are the same, right? Or these two G's are different?
Sorry, there's no G here, right? Those are Q's? Sorry.
Yeah, the G. So
where? Oh, this one?
Yeah.
Yes. Sorry. So the G, thank you. Maybe I should clarify. So, okay. I guess there's no stick. I don't want to pull it back down again. But so the GH2 here, this one is without the modular boundary condition. This one is for the full two-dimensional hyperbolic plane. And then on that one, we will apply the method of images because, okay, computing it in any other way might be more difficult than just applying the method of images on the one with no restrictions at all. So the one with no restrictions at all, it's a commonly known thing, and that's also why I'm not deriving it. It's just the Green's function for 2D hyperbolic space. And then now we're trying to work through the sum over in the method of images. And I'm telling you the first thing we're going to look at is the one for the identity element. And this will have no oscillations. And hence, you will be able to identify it with the mean density of states. Thank you for the question. OK. So I'm not going to do the computation, but it's straightforward integrals just to win a bit of time. So what you want to do, right, is compute. We're using this formula here with the G that we just derived for the full hyperbolic plane, and we'll apply it for Z equals Z prime and G equals 1. Okay. And of course, we're not going to, so this is the normal volume measure on 2D hyperbolic space. And the thing we're going to integrate here will be only on the fundamental domain. because otherwise we're clearly overcounting, right? We're already accounting for the other images by applying G here in the whole sum. Okay, and so in this case, of course, D will be equal to 0, so the cosh will be equal to 1. And you plug that into this formula here. I don't know if you guys see it. Probably you do. And you use this integral representation. So then, okay, I'm going to write it out, but I might mess up the signs and or the factors of 2, or square root of 2. But you end up with something like this to compute. So here note, oh. So I'll have to bring it back down, I made a mistake. So this here is not 0, it's D, which is what's making the whole thing a bit complicated to compute. So this is D as a lower bound and not 0. But in this case it's 0 because D is 0, okay? So here it is actually 0, and we write down the rest. Of course, because of the imaginary part, this will turn out to be the sine part, because of this imaginary here. And you have to compute this integral over R. Okay, and you can compute this, and you'll find that it's equal to 1 over the square root of 2 times pi times, oops. Okay, and so this immediately gives you, like this is just the area of the fundamental domain. So you find something, I don't want to write down the numerical factors to not mess them up, but you can have a go at it and it'll be written out in the notes. You find in that way the area of the fundamental domain. Well, you should find as a numerical factor 1 over 4 pi, and so I actually did write it. And you find this here. Okay, so this formula, if you've ever seen or worked with averaged energy density of states, sorry, that's average density of states of billiards, this is a very common formula. Whenever you send k to infinity, this tangent goes to 1, and you recover what is called the Weil formula, which is a formula that describes in the semi-classical limit the average density of states, or at least the first contribution to it. In general, you would have many more correction terms, and I'll make a comment after writing it down here. So the Weil formula, typically the leading part looks like, indeed, the area of the domain over 4 pi. And so as I was saying, usually you have some corrections. Like usually in billiards, the next to leading correction is about the length of the billiard, like the circumference. But in our case, you find this formula, and again in our case, the corrections are typically corrections in k, right, in the semi-classical limit. But in our case, as I said multiple times, we're not doing some small h-bar expansion. We're not doing a semi-classical expansion, but we will be missing some terms. Specifically, we're looking at the identity now, and the other things we'll take into account are the periodic orbits, because I want to get to this oscillatory part. But the modular group actually has also some other elements, namely, well, matrices with other traces than bigger than 2, and those are like called whatever, elliptic elements, depending on the value of this trace. It's not super important, but there are definitely other elements in this sum we're not going to look at, because they're not giving the contributions that we care about. We care about the d oscillatory part and hence we will only be looking at periodic orbits. Okay, so that's just a disclaimer. And the other elements might give corrections to that. Usually if you look at the Weil formula for specific billiards, you'll find that this is only the leading term. And in fact, if you expand this in powers of k, because so if you look at corrections to this k to infinity limit, it doesn't quite correspond to what you expect from billiards. So clearly you have to take these other terms into account somehow, but it's a bit technical. I don't even know exactly how to do it, but there's definitely papers that do. Okay, any questions about this? So that's the average part, the part we don't care about for our purposes. And now we're going to look at the periodic orbits. Okay, any questions? So it's not super complicated, but there is a bit of a trick to know how to group the geodesics. How to group the matrices G so that the computation is actually not too hard. And of course, because we're talking about periodic orbits, what we will do is split the sum that I just erased, the sum over matrix elements G, so the sum in the method of images. We're going to group the G's into the conjugacy classes. And as you may or may not know, conjugacy classes partition the group. So it's enough to just consider a sum over conjugacy classes, and in each conjugacy class, consider the sum of its elements. Okay, so we will split the sum over G modulo the fact that, of course, we are only going to look at the hyperbolic elements, because these are the ones that lead to periodic orbits. And we're going to sum over conjugacy classes and sum over the G inside each of these conjugacy classes. Okay? Okay, so as a reminder, did I erase everything? Yeah, probably shouldn't have. As a reminder, right, we want to compute. What should I write? Stupid. Should have let it. So ultimately, what we want to do is do some integral over the fundamental domain of some function that is a function of the distance between Z and G acting on Z, right, and everything at some energy. If we do the sum here, what we're going to look at is, instead of, I'll make some space, instead of just looking at G, we're going to look at a sum over S. So suppose we take a G, and we're going to look at its conjugacy class. So we'll sum over all S's so that we run over all the elements in the conjugacy class of G acting on C. So that would be the second sum here. So we're considering one conjugacy class, and this sum here is what we're after. And this function f is, well, you can deduce what it is by looking at the notes. Okay, so at this point it will be a bit abstract. I just want to tell you how to organize the computation in terms of these conjugacy classes. And then once we know this, we'll write down what this f is, and we will, well, not work through the details, but I'll give you the answer. And in the tutorials, we might work through the details. Okay, so then the question is, how do I run in an efficient way over all the S's here? The issue, right, is that I don't want to be overcounting, so I cannot run over all the possible s's because I'll be overcounting. Some of the g's might be sent to a given group element by 2 such s's. When does it happen? Whenever this s is, sorry, maybe I should write the -1 here. Whenever this s here is some g times some other s, where this g here commutes with, when this g prime commutes with this g, because then they will cancel, and then applying this s here or this s prime here will give you the same element. So you know that such elements that are connected by an element that commutes with g, you don't want to include both of them in this sum. You'll be overcounting. So this is an element of, well, this commutes, because I don't know if it's commutant or commutator or whatever the name is. So these g's here commute with g, and we want to mod them out. So that means that we have to consider the let's call the set of all such elements, let's call them SG, all the matrices that commute with G. We want to consider the group P SL to Z as the union of the right cosets of SG. G. Does that make sense to everyone? Okay, so that makes it a bit simpler. We know that in each of these cosets, we just need one representative, and that's the one we will take to run over in a sum. And then, okay, then you can write this here as, well, I'll just write it again. As element of, well, PSL2 Z, and then like the quotient by SG basically. But what I mean really is the right coset. So you can just easily show that this is a subgroup. This guy is a subgroup by this property, by this defining property is a subgroup of PSL2Z. So you can consider the quotient. And then you write down this integral you want to take. Okay, so one last piece of information we need to make the argument is the fact that we want to write this thing a bit more neatly. And how do we do this? Well, we simply use the fact that this distance measure here, it's computed using the metric on hyperbolic, two-dimensional hyperbolic space. And this metric is invariant under any of the PSL2Z transformations, right? It's just a fractional transformation, and that's part of the isometries of the two-dimensional hyperbolic plane. So we know that this is equal, this D here is equal to SZ, comma, right? You just applied Z on both sides, and because this is an isometry of the two-dimensional hyperbolic space, these two things are equal. But now you can see that actually this and this is the same. So you can, instead of integrating over dz here, sorry, is there a question? Instead of integrating over dz here, you can integrate over something that you'll call y. The sum is exactly the same as before. But now here you'll write s, so y is equal to s of z. So right, so you want to integrate over y now. And that is given by this. Oops. Sorry, y. Okay, So all this algebra is just to notice that this sum here, you can rewrite its effect as summing over different domains instead of having the s's being important here. So you can remove their effect here and replace them by just having to sum to make the integration over some different transform domain. Okay. Okay, so if there's no questions regarding this, then you could wonder, okay, what is this domain, right? It turns out it's not super, like if you take the union of all of them, because the sum now is not anymore in the integrand, it's only in the regions you're integrating over. So you might as well just say that you're removing this sum and considering the union of all these domains, right? It's exactly the same. Just summing over, like, because the integral is basically a sum. And you could wonder, what is this domain? Can I understand it geometrically? And the answer is yes. The point being that the group here is equal to the union of all the cosets of this group. So basically the multiplication of any of these elements that commute with G with all of these S's. So if you consider the fundamental domain, all these S's will map the fundamental domain to different places in the upper half plane. But you know that if you also include these, you map the whole upper half place. So that means that the quotient by this group is nothing but the fundamental domain of this group. Okay, so maybe it requires multiple sayings of this sentence, but it's sort of very intuitive. You want the union of all these domains, and all these S's you obtain by modding out by this group. So to reach the whole upper half plane using only this domain, you need all of these guys to act on this domain. So this domain, that means this domain is just the fundamental domain of this group. Okay? Well, if it's now not clear, just think about it at some other point, and it should make sense at some point. So the point is now that whatever we wanted to compute the integral of for each of these conjugacy classes, we'll look at a G and we'll compute. Well, we'll have to think about what the group is that commutes the group formed by all the elements that commute with this G. And once we have it, we just have to compute this fundamental domain and compute whatever we computed here for the identity on some different domain with the right distance, which will not be 0 anymore. Okay? Any question?
One question.
Yes.
Is that construction into cosets general construction, or just it only applies to some certain groups? Is it?
Well, I mean, what we used here, right? I mean, I don't know if you have a specific situation in mind, but what we used here was quite generic, right? I mean, it's a very specific setup also where you're computing. But I guess you could, if you're using the method of images to compute this for any discrete group, for example, of SL to Z, I think you could just apply it to any of them. Because the steps are, I mean, they're just algebraic steps up to now, right? No, I don't think so. But okay, so the last piece of information that I'll give you before we move on to writing down the thing we want to compute and so on, is the fact that if you want to know what this group is, I'll just tell you that the elements in S of G are nothing but elements that can be written like this, where n is elements of the integers, and this G naught is something you have to determine. So it'll be basically some G naught, such that G is equal to G naught to some power K. So K could be 1, and then G naught is just G. But the claim is that all the matrices that commute with G can be written as some G naught to some power, where G is equal to the same G naught to some power. Okay, somehow this might seem intuitive. You might try to, I mean, it's definitely intuitive that the group at least contains these elements. It might not be intuitive that those are the only elements you could write down. And I guess if you wanted to prove this, I don't know to what extent you can do it easily, but I guess trying to map G on the using some PSL2R transformation onto the vertical axis, having the geodesic on the vertical axis being its invariant. Geodesic might be a first step. That would definitely make things easier to try and prove this. Any questions? Okay, only have 10 minutes left. So I guess the only thing I'll do is try to do the first steps and basically show the answer, because I'm not going to, again, we'll do it in the tutorials, hopefully, if people are interested. But then the spectral form factor, we'll do it tomorrow as a first thing, and then we'll move on to talk about chaos in the wave functions as opposed.
You could just write from the center.
Say again, sorry?
You can take it right from the center, not on the side.
Yeah, I feel like I was pulling in the center, but thank you. I was just not pulling super hard at this point. Okay. Okay, so what do we need? So if we consider a certain G, as we have been doing before, what we just showed is that you can write it as, sorry, write one more step, as the fundamental domain of S of G as opposed to a PSL to C. And then the same thing as here. With, of course, this was for the identity element, right? This was for the averaged one. Okay. So that's what we want to do. And to make things a bit easier, what we'll do, because this G here it's invariant under any of the, if we move the two arguments, it's invariant under any of the fractional linear rotations, right? Transformations, because precisely it's only a function of the distance, right? This is an argument we've been using before. So in particular, you can also, instead of trying to, for generic G, try to understand what the fundamental domain would be of S of G. It might be a bit complicated, so what we'll do is we'll rotate this G to its diagonal form, as we've been doing before. And in its diagonal form, given that G might be equal to some G0 to some power, I'll call it M here in this case, just to stick with the notation I have. Well, I have in my notes, M. In its diagonal form, it looks like this. And note, maybe I didn't stress this last time I was writing something in the diagonal form, but it's only a function of a single variable because the determinant has to be 1, right? And so here we're using the fact that we're interested in S of G, And in S of G, all the elements can be written as G to some power, where n is the element of Z, so also all the inverses and so on. And yeah, okay. And of course, its action on Z is very simple because it's diagonal. That's the whole point of going into this representation of this matrix. It would map once again just to this. Okay. And if you stare at this for a while, you can convince yourself that the action of all these guys, their fundamental domain, will basically be a strip on the upper half plane where the values of y are between 1 and lambda 0 to the second power. Right, by just using, well, basically the reason, right, is that you can, all of these points, you can map to the rest of the upper half plane and foliate it with any of these ends, right? The second power will bring you here, and so on, and then the negative powers will bring you here, okay? So in this representation, it's quite easy to find the fundamental domain of this guy, of SG associated to this guy. And so then you know how to write these integrals. Okay. And I guess I have to sort of stop at this point because all the rest is just trying to compute this integral by plugging in, where is it written? By plugging, well, the expression of the full Green's function in terms of this, and working through the various integrals, which is slightly a bit of a pain. And so we'll keep it in the tutorial for in the tutorial sessions. But are the steps clear? Is there any questions about the steps? Like at this point, it's just some integral you have to solve with, like, the boundary conditions are set. You just have to do the integral. Okay. Are there any questions about how to get there? Yes.
You did the union of right process, right? Is a disjoint union? Am I right?
Yes.
Okay. Okay. Thank you.
Okay. Any other question? Okay. And so then, given that I only have a few minutes left and not enough to start anything, I'll just write down the answer. I should have done that. That's the most important thing. Okay. So, okay, this is the integral you have to solve. And note here you had some oscillatory part, but then because you take the imaginary part, it will just give you a sign, right? That you have to plug into the integrand. And working through the steps, let's just write down what the answer is. And then we can compare with the Gutzwiller formula. And next time we'll just plug that in the spectral form factor and use the multiplicity of the periodic orbits and then at a given length. And then we'll find the exponential growth. And that should be also quick, so we can move on to the chaos in the wave functions after. Okay, so what you find when you go through the pain of doing the integral is the following thing. The G contribution to the G in the sum over the method images to the contribution to the density of states looks like this. Okay, so let me just tell you what the various things are here. So this LP here is the length of the periodic orbits that follows from the G0 as opposed to the G. So it's the length of the so-called primitive periodic orbit associated to this set of elements that are some power of G0. These LPs here without the subscript 0, these LPs are just the length associated to the trace of G as opposed to the trace of G0. So these two things this is different than these two here. And then, of course, the momenta K appear all over this formula as well. And if we compare with the Gutzwiller trace formula, what you find is that it's a very generic thing. So this here is nothing but the period of the periodic orbit as opposed to the length. So the period is a unit of time, the length is a unit of distance. And so to go from one to the other, you divide by the momentum. Okay. So this is this guy here. The cosine is this cosine, where SP is h bar k LP. That's something you can also compute for billiards, for example, and you see that the two match. This just happens to be the action in the case of billiard. So the action associated to the periodic orbit that you're focusing on. And then this thing, I think the only thing I told you the last time was that it has something to do with the stability of the periodic orbit. And exactly for unstable periodic orbits, you would have some singe behavior. And so this singe is nothing but the determinant of the monodromy matrix, which has to do with, I guess here I should write M to match with this notation. And so whenever you compute the monodromy matrix for unstable periodic orbits, you find some singe behavior, just like that. So everything matches, and you find that in this case, just by using the method of images and the fact that you're modding out the hyperbolic space by a discrete group, you can find exactly some formula that reproduces all the features of the Gutzwiller trace formula, but that is exact as opposed to semi-classically valid in the case of these hyperbolic domains. Okay, I think I'm out of time. And okay, let's wait tomorrow to have a look at the spectral form factor. And if you have any questions, please ask. And of course, you should sum over G's, right? This was just for one G. Yep.
What is the dimension of the space when this object lives?
When which object, sorry?
This object you build, it lives in some space.
You mean the like what object? This object? What object?
No, the object. You said you have an object which have stable.
Oh, are you talking about the orbits? Because I was talking about unstable periodic orbits.
Yes.
Okay, so right, the orbits I keep talking about are these things, right? Sorry. So you have the fundamental domain, and you could think about, so here there was my attempt at drawing an orbit, but I completely failed, so I stopped. Because it's a bit confusing with periodic orbits, but then in the notes, of course, I'll make a drawing that's not handwritten, and it will look like something. So the orbits I'm talking about are the orbits on this domain, right? So here you have periodic boundary conditions, so you can write down the trajectories of particles that would move on this domain. And some of these trajectories are periodic, so they come back to the same place with the same momentum direction.
Another are halved.
Say again, sorry?
Another trajectory are halved.
So in this case, all the periodic orbits are unstable, as far as I know, and that's a contribution we're computing of all the periodic orbits that are all of the hyperbolic type, because those are the ones that leave invariant geodesics. Well, sorry, geodesics invariant. And we're computing the contribution of these hyperbolic matrices that correspond to these periodic orbits. And yeah, so whenever I talk about unstable, it's basically because they're associated to hyperbolic elements. So there's a correspondence between, like in this case, for example, with traces of the matrices that you look at. Whenever the trace is bigger than 2, it'll give rise to periodic orbits. Whenever it's not bigger than 2, like whenever it's between -2 and 2, I think, there's just no periodic orbits associated to them. And so that's why we don't look at them, because we're interested in this oscillatory part, which comes from the length of periodic orbits. And all of them happens to be unstable in this specific example. In some cases, like in some other examples, you might have stable periodic orbits, but usually, I guess, okay, maybe the statement is not entirely correct, but I think in chaotic systems, most usually you have unstable periodic orbits.
I don't see more questions. So let me just remind that tomorrow is slightly different schedule. There are 2 lectures after lunch, and then some short break, and we will have snacks and some discussion time also here where we have lunches. So please come and don't make any other attractions if you can in the afternoon. I hope we can still enjoy our group here. And thanks to Marine again, and see you tomorrow.